Again, thanks. Actually, it's my great honor to be invited to join Buffalo Day and to talk about some of my recent research. And the topic is real-time machine learning for MIMO OFDM systems, symbol detection using reservoir computing. Again, my name is Lingjia, and for those of you who can pronounce, you can think, and for those of you who cannot pronounce it very well, you can think about Ninja with L. So I'm currently serving as a director of wireless at Virginia Tech. And this work is in collaboration of Dr. Li Zhongzhen from MIT. All right, so let's a little bit talk about, since we talk about machine learning, and let's talk a little bit about why we want to use a machine learning or AI in general to wireless communication systems. So we see actually three major motivations. One is because of the network becomes more and more complex. And so it becomes very difficult to let's say, hand tune, right? Manually tune those various parameters. So it's actually, machine learning can provide us a very good way to actually handle those type of complexity issue. And also another issue is more related to model deficit. So traditionally communication, we're using models to model the system, and then we derive so-called optimal solutions. But we all talk about just now, Jose, when we talk about high frequency, right? I mean, there's a lot of non-linearity, non-perfect of this device. So it's very difficult to analytically characterize our model. It's very difficult to have an analytical model those behaviors in a tractable way. In that sense, machine learning can provide us some benefits. Another thing we see is the algorithm deficit. That being said, even in many simple cases, we know what is the optimal solution, for example, maximum likelihood. But on the other hand, those kind of strategies or algorithms are extremely complicated and to be implemented in real life. So everybody knows actually dirty paper coding is optimal for broadcast channel, right? But on the other hand, what we do for, let's say, MIMO, multi-user MIMO systems in LTE advanced, even 5G systems, they're using still zero forcing based, right? I mean, still very linear based approach because of complexity. Okay, so this is one of the things we can see that machine learning or AI can potentially help. All right, so now let's look at actually different layers and applying machine learning and AI strategies. So there are different layers we can apply, and to me, I'm more like a finite MAC layer person. So we think actually finite MAC layer, foundational layer of wireless network. So we want to look at whether machine learning can provide, let's say, help in finite MAC layer. And in the finite MAC layer, what we see are major issues are model deficit and algorithm deficit. So basically, this, especially in the high frequency domain, right? Non-linearity, device imperfection comes to play. Machine learning can help, and also the algorithm side. And some of the important use cases we can see in the finite MAC layer is related to channel estimation prediction. You can use supervised learning, or you can use receive processing, signal detection, and also channel decoding, and the spectrum access, which you can apply reinforcement learning. So in this particular talk, we focus on receive processing, which is on signal detection side. All right, so since we mentioned about it's good to apply, let's say there's some benefits of applying machine learning or AI to wireless communication systems. There are also a lot of challenges, issues. These are some of the issues we listed, and 5 challenges, and I don't want to go through every one of them, but I want to specifically highlight 2 issues. One is the training issue, another is uncertainty and generalization. So the training issue comes from the play that, I mean, in communication systems. So if we teach communication 101, right? The first thing we're saying that what is the purpose of communication? Is communication unknowns, right? Communication unknowns from the transmitter to receiver. And when we define information, right, that's actually unknown is uncertainty. Uncertainty is actually when we define information, measure of the information. So by nature of communication, we are sending things unknown to the receiver. So, but on the other hand, in order for you to train a neural network model or AI model or machine learning model, so we usually need to send things which is known, right? Those are more like treated as overhead. Unlike, let's say, computer vision applications, communication, the training, especially over the air training, is very, very precious. Okay, so we want to minimize the number of training. And another thing I want to mention is that uncertainty generalization, because we want to make sure the training and testing have the same features. So otherwise it won't work. But unfortunately for communication systems, it's actually very dynamic. Not to mention about the channel is dynamic, the environment is dynamic. For example, for LTE systems, for 5G systems, scheduling is done on a millisecond basis. That means on a millisecond, we are going to have interference, multi-user interference, and everything will be different. So in that sense, how to ensure uncertainty generalization, right? These are actually some of the top challenges we see. All right, so next, let's look at let's focus on the, let's say, signal detection problem. Okay, it's a receive processing. So what we traditionally do is that we use model-based approach. So this picture shows you send X as transmitted, then goes to the channel, and you get Y. And from the received Y, you want to know what is X transmitted. right? That's actually a simple detection problem. So the model-based approach is that usually you model the relationship between X and Y. So you have Y equals to some X, and then you actually do kind of, these are the resource grid for OFDM systems. So these are the actual pilots, these are the actual data. So those white up data. So what do you do that time? You from the pilot, you receive, you actually estimate the channel. And then you look at those data symbols, and then using the estimate channel receive signal, you detect actually what is the symbol detected. Okay, so this is a kind of two-step approach for model-based strategies. So in this slide showing you kind of a procedure for doing this is that you usually assume a model, y equal to hx plus n to start with. And then you say, oh, let's do the pilot, and then we estimate h hat. And based on the pilot, which these are the tildes are based on the actual pilot and receive the signal corresponding to the pilot. And the various methods you can use, least square or linear minimum least square array method. And then from your estimated edge and the receive signal from the data, and then you figure out what is the transmitted signal. Okay, so this is a two-step approach. And then the assumption that, what if the world is not ideal, right? If it's ideal, we have a model. What if we don't have a model? We don't have, what if it's not ideal? Then we make it ideal. What does that mean? We use a lot of strategy called DPD, right? Pre-distortion to trying to make sure the channel or the overall input-output relationship look like kind of linear, right? We pre-distort it first. All right, so is there any other things we can do? Yes, we can potentially using machine learning or learning-based approach. So the learning-based approach is that if you look at this, what happened is that we know what are the pilots, right? Associated with, so the receive signals associated with the pilots, we know it. So what we can do is that we can feed those receive signals into a so-called neural network or machine learning, and then let actually train a model such that it will give us the output of the X, because those pilots we know, those are trainers, right? Then in that sense, we don't need to assume what is the input of our relationship. What we need to only is that train the neural network such that you do the reverse operation, right? F inverse, no matter what F it is. So this seems that, at the first glance, machine learning seems to work, and neural network-based approach should work. And what are the possible issues? The issues is that we need a large amount of training data to train the reverse function, right? And also, potentially, people saying that we can use offline training. Okay, we can use a lot of offline data to train it, and then make it work online. So these are actually some of the arguments. So what are the issues? So let's look at, this is a simple example showing you actually what are the pilots, what are the reference signals in LTE advanced systems, and in the 5G NR systems is similar. So this is a resource grid for OFDM systems. These are the pilots, these are the data symbols. You can clearly see that the number of pilots used in OFDM systems is very small. Okay, it's usually less than 20% or even so in fact, actually, I was a 3GPP standard delegate in from 2008 to 2011 when I was participating or even leading Samsung's work on LTE Advanced. And the moving from release 8 LTE to release 10, release 9 is a small release, to release 10 LTE Advanced, the first thing we did is that we cut the reference signals. We cut those trainings by, okay, in that sense, without doing anything, if you reduce the training, you get system performance improved for the data. This is give you an example of Wi-Fi systems. So Wi-Fi systems have this long training sequence and short training sequence and pilot. And the thing I want to bring awareness is that we have very limited pilot among all the subcarriers, right? We have 48 subcarriers for data and only 4 subcarriers for pilot. All right, so this is actually the reality. So in order for us to apply machine learning, it seems that we should utilize only very limited training over the air, right? And then the key question is that why can't we use offline training? We can use actually a lot of offline data. Let's train it and let's hope it will work online. So what are the issues with that? The main issue with this is that unlike, let's say, so the channel is changing very rapidly over the time and frequency. And on the other hand, if you talk about cellular systems, which we are mainly talking about 4G, 5G, right? All those are cellular related systems. There are a lot of operation modes. And the operation mode is actually changing on the fly. And it is changing on a millisecond basis. And also, even for your unlink, link adaptation, rank adaptation, if you do MIMO, rank from 1, 2, 3, 4, right? And also link adaptation, you have QPSK, 16 quant, 64 quant, even higher order modulations. So they adapt on the fly, and meaning at least on a millisecond basis. So in that sense, it's very difficult for you to train offline and hope it will work online, unless your offline data capture all those features, which is almost impossible. And that means actually if you completely rely on offline training for receive processing, and hopefully it will work online, it can be dangerous, and especially related to the issue I mentioned about uncertainty and generalization. Now the key question becomes, how we are going to make it online? How can you do it online training based on so many limited data, right? I mean, so many limited training, and to make it work and even beat existing communication systems. So the trick or the secret ingredient we use is something called reservoir computing. Okay, so the reservoir computing presents a novel way of looking at computation. So it has three components: echo state network, liquid state machine, and delay feedback reservoir. So what we look at here is that reservoir computing has been used, let's say, in the speech recognition and various actual contexts other than communication. And in the communication side, we are one of the first group actually apply reservoir computing into communication systems. And what makes reservoir computing special is that if you look at this echo network, with a very special network, reservoir computing, is that it has three layers. You have input layer, you have the internal reservoir layer, and also you have output layer. So among these three layers, and if you look at how many weights matrix, there are 4 weight matrix: input weight matrix, internal weight matrix, output weight matrix, and feedback weight matrix. So among these 4 weight matrices, there's only 1 weight matrix, which is actually output weight matrix, are trainable. All other things are fixed, random and fixed. Okay, so this is the internal actually driven. So looking at this, it tells you that, right, I mean, because 3 of the weight matrices are randomly generated and given and fixed, so the training only need to train on the output weight. Okay, so that's actually the beauty or the merit of this. So of course we can discuss a little bit more on why it works, and but we first let's say apply this to, let's say, symbol detection problem. So we have been applied this to OFDM systems, and then we extended it to MIMO OFDM systems, and also this is actually for the MIMO OFDM systems, and then we actually apply this to, let's say, multiple streams. So MIMO OFDM with actually 4 data streams. And this is actually, and later on, we also extended this to, let's say, time frequency. RC, basically, we extend the reservoir computing, the sinkhole, let's say, shallow network into actually a deep network, where actually we take advantage of the time frequency structure. We do it in the time domain and the frequency domain and chain interchange. This is our RC net we introduced. And at latest work, what we do is that we also take advantage, not only looking at the time frequency structure of the OFDM, do the time processing and the frequency processing, and also extend it to take advantage of the modulation structure. Because if you look at those quantum modulations, so we can decompose into the binary actually detection problem, and then we can do the weight sharing, actually significantly improves the, let's say, sample efficiency of this type of systems. So let's look at actually a simple example. What we showed here is that we're using 3GPP 3D channel, which is not, let's say, really fading-based models, and we evaluate for 4x4 channel. And we can clearly see that this RCnet, RC struct is our performance. This is LMMSC, MMSH CSI. That means we're using LMMSC, the channel estimation. We do the LMMSC to do the symbol detection. Okay, 2-step approach. And this is actually the, let's say, sphere decoding based approach. So basically using LMMSC to the channel estimation, then we do a sphere decoding, which is actually, let's say, complexity wise is high, but it's approach to maximum likelihood. You can clearly see even in the, let's say, the regular regime, our method, signal neural network based approach, let's say, can beat existing signal processing based approach. Okay, MNet is existing, one of the existing, let's say, neural network based approach. And this is in a nonlinear region. In the nonlinear region, you can clearly see that, I mean, that's in the power amplifier in the nonlinear region, where signal processing based approach will collapse. On the other hand, actually, neural network or machine learning based approach will still work. So all those things is based on actually training on using the limited, so training using the limited reference signal using within the software. So comparison is fair in the sense of these signal processing based approach. We're using that pilot to do the channel estimation. We are using that pilot to do the training of the neural network. Okay, so this is actually showing our method will work even for rank adaptation and link adaptation. So basically, the system is adapted on a millisecond subframe basis. Each subframe is going to change rank, change link based on the channel condition. So this we are just showing it completely, it can work on the fly. And on the other hand, we also actually extended one more step. So instead of, so previous is online learning, basically on a subframe basis. Okay, so we take the pilots within a subframe and then using that to train, and then detect on a subframe within that data within that subframe. On the other hand, we also actually extended to real-time learning, meaning actually symbol by symbol. So instead of actually wait to receive the whole subframe, you actually do a symbol by symbol detection. Basically, you only make decision based on this OFDM symbol. Okay, so instead of locking, let's say, future symbols within that software. So this is, we are saying that we can actually do a real-time learning, and the neural network weights based on each OFDM symbol basis, which is actually much less than 1 millisecond. And the capacity, we will be able to track the dynamic environment of the channel. So this is, we're using a Wi-Fi as a test, as a simple example, to show that, we can develop our neural network-based approach for Wi-Fi systems, and we are going to detect each symbol based only on these 4 pilots, and then declare next symbol based on the new 4 pilots, update the weights. So not only we did this in analysis, we also put this in the SDR, soft-defined radio, and this is actually, we use a standalone, that's a traditional Wi-Fi transmitter. We don't do any change on the Wi-Fi transmitter. We only do things on the Wi-Fi receiver, and we compare various methods. So in order to have an apple-to-apple comparison, basically, we don't increase any offline. There's no additional training used. So this is actually showing you the neural network-based approach is beating actually existing Wi-Fi signal processing-based approach. And we also extend this to FPGA and real time. So, this is a prototype we built. This is FPGA board, and this is actually what we show, the hardware-based USM. This is a 11 bits fixed point, and performance slightly worse compared with the software-based, but still actually it's not that bad. And we also extend this to multi-user MIMO. And this is actually, we conduct a testing in a dorm because of pandemic. This is actually where students put in his dorm, and we do the transmitter and receiver, and this is actually without shows. So you can see that actually our method, let's say, in a complex real-world environment, we still actually can perform decent, beat actually existing MMSC-based interpretation. All right, so this is the conclusion. So we introduced reservoir computing into MIMO FDM systems for real-time simulation. And instead of doing two-step approach, we can do it one time and also enable online and real-time machine learning. And there's some interesting observations. We see that actually the neural network-based approach can even beat actually MMSC-based approach in the linear region and nonlinear region. And we are able to show that RC-based symbol detection can achieve better image efficiency. So we were seeing that, this is a very good way to, let's say, apply machine learning into even the physical and math layer systems and to have gains. All right, thank you, and that's it.